Since humans first harnessed fire, we've heated things from the outside in. You apply a heat source to the surface and wait for it to penetrate. But the appliance sitting on your kitchen counter ignores that rule entirely. Put a sliced grape inside and turn it on, and it erupts into a glowing plume of plasma. Or take a look at this physical contrast. In the top frame, we have a completely still mug of water that has just been heated. On the bottom, that same water violently boils over the exact instant a tea bag is dropped into it. How does a metal box filled with indissoluble waves bypass an object's surface to trigger explosive reactions, all without a single traditional heating element? The answer to these kitchen anomalies relies on a specific quirk of physics that bypasses the laws of thermal conduction entirely. The process starts with a device called a magnetron. This is the copper anode block of an original cavity magnetron from 1940. This diagram shows how the magnetron acts as an engine. It generates high-frequency electromagnetic waves, specifically at 2.45 gigahertz, and blasts them into the metal cavity of the oven, where they rapidly ricochet off the walls. Those bouncing waves are hunting for a specific target, polar molecules. Water is a prime example. It has distinct positive and negative ends, acting almost like a microscopic magnet. As the electric field from the microwaves alternates, it forces those polar molecules to snap to attention. They spin and flip back and forth millions of times a second, colliding forcefully with surrounding molecules. That intense internal molecular friction generates heat. In physics, this process is known as dielectric heating. By bypassing the exterior and forcing the material to generate its own friction from the inside out, dielectric heating operates independently of traditional conduction or convection. This internal friction explains our earlier anomalies. When you heat water in a smooth glass container, there are no rough spots, known as nucleation points, for bubbles to form on. The water heats internally past its normal boiling point, storing volatile energy until a foreign object is introduced, causing an explosive burst of steam. The grape operates on the exact same dielectric principles, but with a structural twist. Looking at this data visualization, you can see how the physical size of the grape halves forms a resonant cavity. They funnel and trap the 2.45 gigahertz waves into a microscopic focal point, generating an electric field so intense it strips electrons directly from the air, forming plasma. If these waves are powerful enough to strip electrons and superheat liquids, it raises a fairly obvious safety question. Why don't they escape through the glass door and cook the person watching? The protection comes from a built-in Faraday cage, visible as metal mesh inside the glass door. This scale comparison illustrates exactly how the cage works. The microwaves operate at a wavelength of about 12 centimeters. The holes in the mesh are only 1 to 2 millimeters across. Visible light easily passes through the gaps, letting you see inside, but the massive 12-centimeter microwaves physically cannot fit, forcing them to reflect back into the oven. Trapping this violent friction inside a sealed, shielded box turned the magnetron into a household staple, but the utility of this force reaches far beyond the kitchen. The earliest commercial units, like this massive floor-standing Raytheon Radarange, were heavy industrial machines. As the technology eventually scaled down for consumer use, engineers also scaled it sideways for manufacturing. In manufacturing, inside-out heating is used for electronic sewing. Instead of applying a hot iron to the exterior, engineers use radio frequencies to excite the molecules within plastics, fusing them together seamlessly from the inside. In the medical field, we see tools like this modern diathermia machine. It uses targeted radiofrequency heating to safely penetrate and warm deep muscle tissue for physical therapy without burning the skin. Advanced hyperthermia treatments take this a step further. Doctors use the exact same concept to target and cook cancer cells from the inside out, making tumors far more susceptible to radiation and chemotherapy. The ability to pinpoint and alter internal structures without damaging the exterior surface has proven to be an invaluable tool for both engineering and human health. But perhaps the most delicate application of dielectric heating takes place in the world of art preservation, where conservators work meticulously on masterpieces like Michelangelo's David. For centuries, historic marble sculptures have faced a slow threat from microscopic fungi colonies that settle into the porous stone and eat away at the surface. To fight back, researchers have turned to the exact same 2.45 gigahertz frequency generated by your kitchen microwave, using specialized wands to direct the waves directly into the stone. The invisible waves gently heat the marble from the inside, just enough to kill the destructive fungi colonies. It requires zero harsh chemicals and poses no risk of physical damage to the delicate outer layer of the sculpture. The precise molecular friction that ignites a grape and warms your morning coffee also heals human tissue, drives modern manufacturing, and quietly preserves our history.